In this lesson, we are going to define the purpose of the Directional Gyro Indicator, or DGI, and look at its construction and principle of operation. The DGI is sometimes referred to as the Direction Indicator, or DI. We will also look at the errors which the DGI is subject to and how the effect of the errors is reduced. The DGI provides a stable directional reference in azimuth for maintaining accurate headings and carrying out accurate turns. A typical DGI display is shown here on the right. A less common display is shown on the left. Note that although the DGI display consists of a compass rose, the DGI is not a magnetic compass instrument and is therefore free from the acceleration and turning errors of the direct reading magnetic compass. To be of value, however, as a source of heading information, the DGI needs to be continually synchronized with the magnetic compass, and we will see why later in this lesson when we consider the errors the DGI is subject to. An example of the internal workings of an early air-driven DGI is shown here. The DGI uses a tied gyro, which has 2 degrees of freedom. The rotor spin axis is maintained in the horizontal, or yawing, plane of the aircraft. The lesson on gyroscopic theory looked at the properties of gyros. Note that in the DGI, the gyro rotor is mounted in the inner gimbal, on bearings mounted in the outer gimbal. The outer gimbal can rotate through 360 degrees around the aircraft's vertical axis on bearings within the case of the instrument. Note that the rotor spin axis, the inner gimbal axis, and the outer gimbal axis are mutually at right angles to each other. During a turn, the aircraft and the instrument case turn around the vertical axis bearings of the outer gimbal, while the spin axis of the gyro rotor remains fixed in azimuth because of gyroscopic rigidity. In the example shown here, the heading is indicated against the cylindrical indicating scale by a lubber line on the glass window in the instrument case. The more common type of display used in modern aircraft can be seen here on the right. With this type of display, the cylindrical indicating scale is replaced with a vertical card compass rose, which is geared to the outer gimbal. The air-driven DGI incorporates bucket-like features around the perimeter of the gyro rotor, and an engine-driven pump creates a partial vacuum in the instrument case, which allows cabin air to be drawn in through an air jet, or in some cases twin air jets, to drive the gyro rotor, as we can see here. The air jet not only spins the rotor, but also maintains or ties the rotor axis in the yawing plane of the aircraft. The way it works is that so long as the rotor axis lies in the yawing plane, and therefore at right angles to the outer gimbal axis, the full force of the air jet will be used to drive the rotor. We will call this force X.
If the gyro topples but the aircraft stays level, the rotor is no longer in the yawing plane of the aircraft, or at right angles to the outer gimbal axis.
As the air jet is fixed to the outer gimbal, the airstream now strikes the rotor at an angle. The resulting force can be resolved into 2 components, Y and Z. Component Z will precess the rotor as if the force had been applied at a point 90 degrees around the circumference of the rotor in the direction of spin at position Q. The effect is therefore to realign the rotor with its axis in the yawing plane. The air jet provides coarse adjustment of the rotor spin axis. Fine adjustment is achieved by a secondary system which involves a wedge plate fixed to the outer gimbal. If we look closely, we can see that the airstream flowing around the rotor is directed at this wedge plate. The wedge plate normally separates the air jet into two equal pressure streams, producing equal reactions on the outer gimbal. However, should the rotor start to topple, the reaction from the airstream on the wedge plate becomes unequal. The effect of this unequal reaction is to apply a sideways force to the outer gimbal, which is transmitted to the inner gimbal. We will call this force F. Force F is precessed by the gyro 90 degrees in the direction of rotation to location P, as we can see here, and this finally adjusts the rotor and inner gimbal back into the yawing plane. On the front of the instrument, there is a spring-loaded caging knob. When the knob is pushed in, the inner gimbal is physically moved to maintain the spin axis of the rotor in the yawing plane. At the same time, a gear engages in the outer gimbal so that by turning the knob, the gyro can be rotated to synchronize the DGI compass rose with the magnetic compass. So the uses of the caging device are firstly to reset and synchronize the DGI with the magnetic compass, secondly to engage and lock the gyro rotor to prevent topple while the gyro is being synchronized, and thirdly, should the gyro be subject to topple, the caging device can be used quickly to re-erect the gyro. It is worth noting that if the aircraft is subjected to excessive pitch and roll, the gyro will topple unless it is caged to prevent internal damage. The uncaged manoeuvre limits for an air-driven DGI are plus or minus 55 degrees in roll or pitch, and plus or minus 85 degrees in roll or pitch for an electrically driven DGI. The DGI suffers from a number of errors. The main errors we will look at here are gimbaling error, real wander, which is sometimes referred to as random wander, earth rate, errors caused by the effect of incorrect rotor speed on the latitude nut. We shall explain what the latitude nut is shortly, and transport wander. Let's look at each of these in turn. There are errors in the indication of the DGI, which occur whenever bank or pitch are applied. Here is the gyro and its outer gimbal in level flight. The inner gimbal has been removed for clarity, but it is always in line with the gyro axis. The aircraft is flying towards the bottom left of the screen, as you see it here. If the aircraft now banks to its right, the gyro axis and the inner gimbal stay level, but the outer gimbal banks with the aircraft. The aircraft will start to turn. Gimbaling error is caused because the aircraft is rotating about its own yawing axis, whilst the inner gimbal stays level. The outer gimbal ring must move. These errors become even more complex if pitch is applied. Examiners sometimes refer to this error as being caused by applying pitch in a turn, although they occur in any bank turn. Gimbaling errors are small if the attitude deviation from level flight is only moderate, and they disappear as soon as level flight is resumed. Real wander occurs as a result of imbalances, uneven wear, and friction in the instrument itself, and will be specific to each instrument. When it comes to calculations, therefore, the figure for real wander will be given to us. Otherwise, the gyro will be stated as being a perfect gyro, which means that the gyro is free from real wander. Watch out for this. The fundamental reason for apparent wander is dealt with in detail in the lesson on gyroscopic theory, and as we have seen, the DGI will be subject to apparent wonder from both Earth rotation and transport wonder. To assist our understanding of the DGI, we will look briefly here at the cause of apparent wonder. Apparent wonder is said to occur whenever the spin axis of a perfect gyro appears to an earthbound observer to be changing direction. One of the properties of the gyro is its ability to maintain its spin axis in a fixed direction in space. So with this in mind, a way to envisage the effect of apparent wonder on a DGI is to imagine a compass rose pointing towards true north at position A. If we now superimpose a DGI compass rose and align it with true north also, we can see that during the course of a day, as the Earth rotates on its own spin axis, the bearing of true north relative to the gyro north changes. In effect, the direction in which the gyro is pointing remains fixed in space, but to an earthbound observer, it is the direction of true north which remains fixed. It will appear to the observer, therefore, that relative to true north, our DGI reading has decreased. This is known as apparent wonder due to Earth rate. Note that apparent wonder only occurs at latitudes other than the equator. In the northern hemisphere, the Earth rate is designated as negative or minus for the purpose of calculations, and it is positive or plus in the southern hemisphere. The formula to note for Earth rate is Earth rate equals 15 degrees times the sine of the latitude in degrees per hour. Apparent wonder due to transport wonder will occur at the same time as Earth rate. In the case of transport wonder, however, the additional factor is that the gyro itself is moved across the Earth. Although Earth rate and transport wonder occur at the same time, when we come to do calculations, we calculate the error for transport wonder separately and add or subtract it to the equation for total wonder. We will look at this in more detail in the companion lesson on drift rate calculations. Note that transport wonder occurs when the gyro is transported in an easterly or westerly direction across the Earth at latitudes other than the equator. At the equator, transport wonder will be 0. It will also not occur on flights along a north-south meridian. The formula for transport wonder is transport wonder equals the easterly component of ground speed divided by 60 times the tan of the latitude in degrees per hour. For the purpose of calculations, transport wonder in the northern hemisphere is designated minus in an easterly direction and positive in a westerly direction. We will look at a simple way to work this out in the companion lesson on drift rate calculations.
Before going on to consider the errors caused by incorrect rotor speed, we need to know what a latitude nut is. We have seen that if the gyro remains in a fixed direction in space, apparent wonder will occur due to Earth rate. The magnitude of the apparent wonder will depend on the latitude, and it is possible to calculate the magnitude.
The purpose of the latitude nut is therefore to deliberately introduce an out-of-balance mass to cause real wonder in the gyro, which will be equal and opposite to the apparent wonder caused by Earth rate at a specific latitude. In other words, the latitude nut will produce an opposite error to that caused by the Earth's rotation. In its simplest form, the latitude nut is an actual nut wound onto a thread on the spin axle of the gyro rotor, which we can see here. At the equator, the latitude nut is central on the thread as no induced wonder is required. As latitude increases north of the equator, the latitude nut is wound out to cause real wonder equal and opposite to the apparent wonder caused by the Earth's rotation. And south of the equator, the latitude nut is wound in to cause real wonder equal and opposite to the apparent wonder caused by the Earth's rotation. It follows, therefore, that as the latitude nut is set for a specific latitude in a workshop and cannot be changed in the aircraft, it will be correct only at the latitude for which it has been set. This may not necessarily be the same latitude as the aircraft's actual latitude. We have now covered the principle of operation and construction of the DGI, and the main errors which the DGI is subject to. In the companion part of this lesson, we will look at a simple way to do drift rate calculations, and we will work through a typical example. A summary of the main points of this lesson follows.
The latitude nut causes precession of the gyro to compensate for earth rate. But the precession of a gyro depends on rotor RPM. Unfortunately, the control of rotor RPM in the DGI is only approximate. For instance, at high altitude, with an adequate suction, the rotor RPM will be lower than the design value. Lower RPM gives lower rigidity, so the precession rate will be too high. This means that the latitude nut correction is too high, overcorrecting the earth rate. In reality, this is more of a theoretical problem than a practical one. The amount of error will be small, and is usually completely swamped by the far greater error of real drift in typical DGIs.
Apparent wonder due to transport wonder will occur at the same time as earth rate. In the case of transport wonder, however, the additional factor is that the gyro itself is moved across the Earth. Although earth rate and transport wonder occur at the same time, when we come to do calculations, we calculate the error for transport wonder separately and add or subtract it to the equation for total wonder. We will look at this in more detail in the companion lesson on drift rate calculations. Note that transport wonder occurs when the gyro is transported in an easterly or westerly direction across the Earth at latitudes other than the equator. At the equator, transport wonder will be 0. It will also not occur on flights along a north-south meridian. The formula for transport wonder is transport wonder equals the easterly component of ground speed divided by 60 times the tan of the latitudes in degrees per hour. For the purpose of calculations, transport wonder in the northern hemisphere is designated minus in an easterly direction and positive in a westerly direction. We will look at a simple way to work this out in the companion lesson on drift rate calculations. The DGI provides a stable directional reference in azimuth. The DGI does not suffer from the acceleration and turning errors of the magnetic compass. The DGI needs to be regularly synchronized with the magnetic compass. The DGI uses a tied gyro with 2 degrees of freedom. The spin axis is maintained in the yawing plane of the aircraft. The gyro rotor is mounted on the inner gimbal on bearings in the outer gimbal. In an air-driven DGI, the use of air jets maintain or tie the rotor axis in the yawing plane of the aircraft. In an air-driven DGI, the nozzle and wedge plate are mounted on the outer gimbal. The formula for earth rate is earth rate equals 15 degrees times the sine of the latitudes in degrees per hour. At the equator, there will be no apparent wonder. Transport wonder occurs when the gyro is transported in an easterly or westerly direction at latitudes other than the equator. Transport wonder does not occur on flights along a north-south meridian. The formula for transport wonder is Transport wonder equals the easterly component of ground speed divided by 60 times the tan of the latitude in degrees per hour. The caging device is used to synchronize the DGI with the magnetic compass and to prevent topple. The DGI maneuver limits in roll or pitch are plus or minus 55 degrees, air-driven, and plus or minus 85 degrees, electrically driven.
DGI errors are gimbling errors, real wander, earth rate, incorrect rotor speed, and transport wander.
The purpose of the latitude nut is to produce real wander which is equal to and opposite to apparent wander caused by earth rate. The latitude nut is set for a specific latitude only.